it's time to tackle our final section of the semester, Chapter 11, Section 5 on binomial theorem. This brings up the Pascal's triangle. Hopefully you're familiar with Pascal's triangle. This is just one I printed off from the internet. I got this at Shodor. You are welcome to just Google Pascal's triangle, find you one that is easily read, and I suggest you print a copy to keep it on hand because it makes work a little bit simpler. Because when we use binomial theorem to do binomial expansions, it just simplifies things. Okay, so binomial expansion. A binomial is an expression with two terms. For example, x plus 2 is what we're using for these three. Now, when we FOIL, we are expanding that binomial to a power of 2. And you know how to do this. This is just x plus 2 times x plus 2. We can kind of do that in our sleep, right? So we have x squared plus 4x plus 4 is our binomial expansion for x plus 2 quantity squared. Well, what if we want to cube this? Well, we could start from scratch and multiply times itself 3 times. Or we could just say, you know what, we've got x plus 2 times x plus 2 squared. We just did x plus 2 squared. So now I'm going to multiply each of the terms in this binomial to all 3 of the terms in the trinomial. So that is going to give me x cubed plus 4x squared plus 4x. And then when I multiply in the 2, I have 2x squared, 8x, and 8. Then when I combine like terms, I have x cubed, I have 6x squared, I have 12x, and plus 8. So that is that binomial expansion. Now when we get over here to x plus 2 to the 4th power, we have a couple of choices. We could do x plus 2 times this x plus 2 cubed product that we just got. Or we could do x plus 2 squared times x plus 2 squared, which is what I'm going to choose. I'm going to have x squared plus 4x plus 4 times x squared plus 4x plus 4. And the way I'm going to do that, the way I'm going to set that up, is by using a grid method because it helps me to arrange things. So I need, because I'm multiplying a trinomial times a trinomial, I'm going to structure a 3 by 3 grid, where along the top I have x squared, 4x, and 4, and then down the side I'm going to have x squared, 4x, and 4 because both of those trinomials are the same. And then I fill in the products working across the rows. X squared times itself is x to the 4th, then I have 4x cubed and 4x squared. On the second row I have 4x cubed, 16x squared, and 16x. And then my last row is 4x squared, 16x, and 16. And you'll notice that the diagonals have the same exponent, so I can add along the diagonals. And the product I get is x to the 4th plus 8x cubed, that's a 16, so that's 24x squared. And then 32x plus 16 for that binomial expansion. Now that's not a lot of work. We can do that pretty simply. But what if you were asked to do something like x plus 2 to the 10th power? Well, if I needed to expand something like that, that takes a lot of effort, right? Because, I mean, we've got x plus 2 to the 4th here, but 4 is not a product of 10. We could do x plus 2 to the 5th, maybe. Anyway, it just gets crazy hard. It takes too much work. Well, there's an easier way to do that using binomial theorem. We call it binomial expansion using binomial theorem, and it takes us to the Pascal's triangle. That's what I suggested you have handy. Also, you're going to need a couple of extra sheets of paper because our pages in our notes here are not enough. We're going to do some extra work, so you'll need some room to spread out. By definition, if I have j and n that are integers such that they're both positive and j is less than n, then this symbol, and I would read this symbol as n choose j, is defined as n factorial over j factorial times n minus j factorial. Oops, factorial goes on the outside. N minus j factorial. Now this hopefully will look familiar to some of you. If you've done it probability anywhere, this is how you calculate the combinations, number of combinations in probability. When you're doing combinations and permutations, you're choosing sets of items. Permutations are when order matters, combinations are when order does not matter, and this definition, which is basically finding numbers of combinations, leads us into our binomial theorem. So we're going to do some of these by hand, and then we're going to use our calculator. I want you to do the ones by hand that I do by hand so that you will have done some practice in simplifying. Alright, so if we have 4 choose 1, n choose j here is 4 choose 1, that is going to look like 4 factorial over, and then I put my j, and then I subtract, and I have 1 factorial, 3 factorial. And if you'll remember from our introduction to factorials, I just need to stop at the largest value. So in my numerator, I can do 4 times 3 factorial because that's going to cancel out. And then 1 factorial is just 1, so that leaves me with 4. On the next one, I have 6 choose 2. So my numerator is 6 factorial, my denominator is 2 factorial, and then 6 minus 2 is 4 factorial. So in my numerator, I have 6 times 5 times 4 factorial. And then I still have this 2 factorial, which is just 2 times 1. I'm just going to write down 2. That cancels and leaves me with 30 divided by 2 is 15. On C, I have 10 factorial over 9 factorial, 1 factorial. So I can do 10 times 9 factorial over 9 factorial times 1. And that cancels and just leaves me with 10. Now, take note that when I did 4 choose 1, I got 4. When I did 10 choose 9, which means there was 1 left, I got 10. Just FYI, keep that in your mind. Now, it recommends to us that we're going to use our calculator here on D. Remember our probability button? 50 choose 10, if I wanted to set it up, would be 50 factorial over 10 factorial, 40 factorial. Well, that's a lot in my numerator to simplify. So I want to think of this as a combination problem, so that I'm doing 50 choose 10, and I'm going to take my calculator and use my probability button. We rolled that out the other day. When I use my probability button, I'm going to type in the 50, that n, first, and then use probability and move over to combinations and choose R, and our J, or our R in this case, is 10. So that's what the screen of my calculator looks like. This is my answer I get in scientific notation because this is a really, really large value. So this gives me 1.027, and then it just keeps going. Let's just leave it there at 3 decimal places, times 10 to the 10th power. We would move our decimal place 10 places back to the right to get that value. So again, some of those big ones that you can't simplify nicely, we want to make sure you use your calculator on. Okay, before we get into this, I want to do a quick little here, pay attention to this kind of thing. Let me fix my light so we don't have a glare. Alright, let's do 5 choose 0 all the way down to 5 choose 5. So we're going to start at 5 choose 0. 5 choose 0 would be 5 factorial over 0 factorial 5 factorial. Hopefully you remember that 0 factorial is defined as 1. So this is just 1 over 1, or 1. When I do, we're going to switch and we're going to do 5 over 1. So 5 choose 1. That would be 5 factorial over 1 factorial 4 factorial, which is, the 4 factorial is going to cancel. That just leaves me with 5. And we're not going to do 5 choose 2 or 5 choose 3. We're just going to skip all the way to 5 choose 4. Notice that I just picked 1 and then I picked everything else here. 5 choose 4 would be 5 factorial over 4 factorial 1 factorial. Notice your denominator. Order doesn't matter with multiplication, so these denominators are exactly the same, which means that is also 5. And then finally, what if I do 5 choose 5? Well, I've got 5 factorial over 5, 0. which again is just exactly the same as 5 choose 0. It is 1, because everything cancels and I just have everything over itself as 1. Now, can you guess if I did 5 choose 2 and 5 choose 3? They are going to give me the same result. Let's do 5 choose 2. That gives me, there we go, 5 factorial over 2 factorial, 3 factorial. 5 choose 3 would be 5 factorial over 3 factorial, 2 factorial. Either way, what I end up with is 5 times 4, 5 times 4, and then the 3 factorial will cancel, so it's going to be over 2, which is 10 for each of those. Some useful things to remember. This is what we just went over. Some useful things to remember. N choose 0 is 1, and N choose N is also 1. Just like we did up here. Choose 0, I get 1. Choose everything, I get 1. N choose 1 is N, and N choose everything but 1 is also N, right here. 5 choose 1 is 5, 5 choose 4 is also 5. So you see that, and then I went ahead and did these other two, you see that these got the same result as well. So you can see that you have things pairing up. Now we're going to arrange this in a triangular pattern. So we've got, we are going to name our rows by n. So that means our first row is n equals 0 because we have 0 choose 0. Our second row is n equals 1. 1 choose 0, 1 choose 1. Then we have n equals 2, n equals 3, n equals 4, and n equals 5. See that your top number in your binomial expression, binomial coefficient, is the number of the row, and then the bottom number is your j. We're picking. Are we picking 0, pick 1, pick 2. Pick 0, 1, 2, 3. For this fifth row, or not fifth row, but n equals 5 row, 0, 1, 2, 3, 4, 5. We're counting across. We're going to find each of those values to create a new triangle. If we do 0, choose 0, anything choose 0 is 1. Then we have 0, 1 choose 0 and 1 choose 1. That fits right here. So those are both 1s for that next row. So we have n equals 0, we have n equals 1. We're going to do n equals 2, 3, 4, and 5. And I hope that I didn't just mess up my triangle shape. We're going to see what we can do. N equals 2. Well, we've got choose nothing, choose everything. We know those are going to be 1s. And then we need something in the middle. 2 choose 1. Anything choose 1 is n. So 2 choose 1 is 2. For n equals 3, our outside numbers again are going to be 1s because choose nothing, choose everything. And if I choose just 1 or choose everything but 1, I have n. So this is going to be 3 and 3 in the middle. When I move to my fourth row, those outside values are still going to be 1s, and they're going to be 1s on the fifth row as well. On the fourth row, back to the fourth row, choose 1, choose everything but 1, always gives me n, so those are going to be 4s. And in the middle I have 4 choose 2. Well, what would 4 choose 2 be? 4 choose 2 is going to be 4 factorial over 2 factorial, 2 factorial. So 4 times 3 over 2, because the 2 factorial cancels out. I'm going to go ahead and put that down there to show it. 12 divided by 2 is 6. And then we did 5s, right? We did our 5s. We got 1 on both outsides, then we got 5 and 5. And then we got 1s, we got 5s. What about these two? Well, we did those two and we got 10s. Now, this is the first 6 rows n equals 0 through n equals 5 of Pascal's triangle, named after Blaise Pascal. And it asks you to notice patterns. Hopefully you have talked about Pascal's triangle before. You recognize that you have the patterns, the ones down the outside diagonals. If you go in this next diagonal, you're adding 1. Here you're adding 2, add 3, add 4, so you're adding 1 more each time. The diagonal, that pattern works either direction. And finally, I add the values above to get the value below. So 1 and 3 is 4, 1 and 4 is 5, 4 and 6 is 10, 4 and 6 is 10, 1 and 4 is 5. Always ones on the diagonals. So lots of patterns in Pascal's triangle. And then we're going to use those patterns to find, now it says the 6th row. I want you to think about that. This, technically, 1, 2, 3, 4, 5, 6 is the 6th row. I want you to find the 7th row where n equals 6 of Pascal's triangle. So if you would, I want you to take a second and pick a way to calculate those coefficients for Pascal's triangle for that 7th row where n equals 6. We know the 1s are going to be on the outside, 6s are going to be next, because that would be n choose, or 6 choose 1 and 6 choose 5. I can also add 1 and 5 is that 6, 5 and 10 are 15, 10 and 10 are 20, and 10 and 5 are 15. So there is my 7th row where n equals 6 for the Pascal's triangle. These are also going to give us what we call our binomial coefficients that are part of our binomial expansion for our binomial theorem. Now we've just got 1 page of notes left, but we're going to do a couple pages worth of work. So like I said, make sure you have an extra piece of paper handy. Okay, binomial theorem. It looks a little lengthy. We're going to fill it in and then we're going to talk about it a little bit. Our binomial theorem, each term has basically 3 parts. It has our binomial coefficient, which we're going to start with n, choose 0. It has this second term, which is usually a constant, and we start with the 0 power and we're going to work our way up for the constant. And then we have our variable term, that first term in our binomial, and it starts with whatever power n is, and it works its way down. So that's the first term, and then for the second term, my binomial coefficient would be n choose 1. A is going to be a to the first, x is going to be x to the n minus 1, because remember my exponent on the a is counting up, my exponent on the n is counting down. And depending on how big n is, I'm going to keep going. We're going to throw in a middle term here somewhere that defines this binomial coefficient as n over j, so that I have a to the j, x to the n minus j, and then we're going to keep going until we get to our last term, which is our constant, where we have n choose n, we have a to the n, and we have x to the 0, which is just 1. That gets us this as the formula that shows me my binomial theorem. Now remember, this n over j is what we call our binomial coefficient. And that binomial coefficient is what we can get from Pascal's triangle. We can either work it out by hand ourselves, or we can go look at the appropriate row in Pascal's triangle to find that binomial coefficient. By definition down here, what do you think it is? These symbols represent the numerical coefficients that appear in a binomial expansion. And so they are true no matter what. They are going to be the same no matter what our terms are in our binomial. Okay, now we're going to switch over, we're going to skip over to our extra page here. Before we do x minus 3 to the 6th, we're going to do a couple of smaller problems. So set this page aside. And let's do, you know what, let's do x plus 2 to the 4th. We already know the answer to that. We already did x plus 2 to the 4th, right? We did that on the very first page of our notes. When we expanded x plus 2 to the fourth on the first page, that's where I used that the grid, and I got x to the fourth, 8x cubed plus 24x squared plus 32x plus 16. So we know that this is our goal for x plus 2 to the fourth. We're going to do it now using binomial expansion. Well, each term has three pieces. They have the binomial coefficient, the second term from my binomial, and then the first term from my binomial. Give me just a second. I am distracted just a little bit from sound in the other room. Okay, so our binomial coefficient, we're going to start with 4 choose 0. So 4 choose 0. And then our a term is 2 to the 0, and then our x term is x to the fourth, because we're starting from 0 with the 2, and we're starting from our largest exponent with the x. Because if you look at what you get in order, you have this as your largest exponent, and you count all your way down to the constant. So when you have a fourth degree polynomial, you have to the fourth to the third squared x and then constant. Fourth degree gives you 5 terms. This is your first term. Your second term is going to be 4 choose 1, 2 to the first, x cubed. Your third term is 4 choose 2, 2 squared, x squared. Your 1, 2, 3, fourth term is 4 choose 3, 2 cubed x, and your last term is 4 choose 4, 2 to the fourth, x to the 0. So those are the 5 terms, 1, 2, 3, 4, 5, in your binomial expansion. Now this binomial coefficient is going to relate to the n equals 4 row of your Pascal's triangle. If I look at n equals 4, I see that my binomial coefficients will be 1, 4, 6, 4, 1. 4 choose nothing is 1, 2 to the 0 is 1, and I have x to the fourth, plus 4 choose 1 will be 4 times 2 times x cubed, plus 4 choose 2, if I need to do a little bit of work here, this 4 choose 2 would be, let's kind of go off to the side maybe up here, 4 choose 2 would be 4 factorial over 2 factorial 2 factorial, which is 4 times 3 times 2 factorial times another 2, gives me 12 over 2 is 6, or I could have used my Pascal's triangle. And then 2 squared is 4x squared, plus 4 choose 3 is going to be 4 again, 2 cubed is 8 times x, 4 choose 4 is 1, 2 to the fourth is 16, and x to the 0 is 1. When I finish this off, I have x to the fourth plus 4 times 2 is 8x cubed, plus 6 times 4 is 24x squared, plus 4 times 8 is 32x, plus 16, which is exactly what I got when we did it the other way at the beginning of the lecture. Let's go ahead and go, you know what, yeah, let's go bigger by 1. Just to, oh, no, we're not going to go bigger by 1 here. We're going to go back to our page. I think we can do this next, right? X minus 3 to the 6th power, that's our binomial expansion that we're going to do here. Let me make sure that we have it delineated. Okay, so if we have a 6th power, we have 7 terms. We're going to start with 6 choose 0, and I'm going to try to remember to move this over because it's going to take me my entire page to show this. 6 choose 0. I'm going to start with this negative 3 to the 0 and x to the 6. That's my first term. My second term is 6 choose 1, negative 3 to the first, x to the fifth. Notice that my exponents always add to whatever this power is. 0 and 6 is 6, 1 and 5 is 6. My next two exponents will be 2 and 4. So I will have 6 over 2, negative 3 squared, x to the fourth, but the sum of the exponents will always be equal to whatever that power is that we are expanding it to. That's my third term. 1, 2, 3 out of 7 terms. Next I have 6 choose 3, negative 3 cubed x cubed. There's my fourth term. 6 choose 4, negative 3 to the fourth x squared, plus 6 choose 5. 1, 2, 3, 4, 5, yep. 6 choose 5, negative 3 to the fifth x, and then finally my constant 6 choose 6, negative 3 to the sixth, and x to the 0. So on each term, the exponents add to the power of the expansion, in this case 6. Okay, so this binomial coefficient, again, you can work it out using either your formula for combinations, or you can look at the n equals 6 row of your Pythagorean Pascal's triangle, so that you know your coefficients, your binomial coefficients are going to be 1, 6, 15, 20, 15, 6, and 1. Now, I'm not going to give you a Pascal's triangle on the exam, so you have to either know how to create the triangle or be comfortable with working out each of these binomial coefficients. It's totally up to you. So this first binomial coefficient is 1, negative 3 to the 0 is 1, x to the sixth. Second binomial coefficient is 6, negative 3, x to the fifth. Third binomial coefficient then is 15. Negative 3 squared is 9, x to the fourth. Next binomial coefficient is 20. Negative 3 cubed is negative 27, x cubed. My next binomial coefficient is 15 again. Negative 3 to the fourth is a positive 81, x squared. 6 to the fifth is 6. Negative 3 to the fifth is a negative 243, x. And then my constant is 1 times a positive 729. All right, let's put this in the terms we need. See, I told you I can't make it all fit. Okay, so my first term is x to the sixth. My second term is a negative 18x to the fifth. And then I have a positive 135x to the fourth, a negative 540x cubed, a positive 1215x squared, and then a negative 1458x, and a positive 729. So that is x minus 3 expanded to the sixth power. Alright, see, not complex, just you have to be, it's fiddly. You have to be careful with your coefficients. Okay, let's do this next one where we have 3y plus 2 to the fourth power. So we're only going to have 5 terms because you have x to the fourth all the way down to the constant. Only 5 terms, but note that you have a coefficient on your y term, so you have to account for that as well. So let's start this expansion with 4 choose 0, 2 to the 0, 3y to the fourth. Notice that 3y is in parentheses. That matters. That's my first of 5 terms. My next term is going to be 4 choose 1, 2 to the first, 3y cubed. That's my second term. And then I have 4 choose 2, 2 squared, 3y squared. That's my third term. 4 choose 3, 2 cubed, 3y to the first. That one's counting down. 1, 2, 3, 4. My last term, 4 choose 4, 2 to the fourth, and 3y in parentheses to the 0 because we have to make sure that that is all 1. Alright, finally, my binomial coefficient. This one is going to be 1, and this one is going to be 1. This will be 4, this will be 4, and this one is going to be 6. We've already calculated it a couple of times, so I can remember that one. So I have 1 times 3 to the 4th is 81y plus 4 times 2 times 27y cubed. Oh, this is y to the 4th, this is y cubed. Sorry, guys. And then this one we said was 6. So 6 times 4 times 9y squared plus 4 times 8 times 3y plus 1 times 16 times 1, because 3y to the 1st is just 1. Okay, when I straighten those out, I've got 81y to the 4th plus 8 times 27 is 216y cubed plus 6 times 4 is 24 times 9 is 216y squared plus 4 times 8 is 32 times 3 is 96y plus 16. There is my binomial expansion for that one. Okay, these last two questions ask you something a little bit different. This one wants just the coefficient of the x to the 7th term. This one wants the 7th term of this expansion. We don't want to have to do the entire expansion just to get a couple of terms. So I want to give you a generalization to help you know what to do in these cases. Okay, so in general, x plus a to the n, when I have x plus a to the n, the term containing x to the j is, and I find it like this, n over n minus j, a to the n minus j, x to the j. So notice that I know which term I'm looking for, that's this power, and the exponent here is the denominator of my binomial coefficient. So let's do an example of that. Therefore, if I have 2y plus 3 to the 10th power, and I want to find the coefficient for y to the 8th, well, I know that my exponents are going to add to 10 in this case because my expansion is to the 10th. So if y is to the 8th power, then this 3 is going to be squared. So what I'm doing here is I'm finding 10 of 2. That's my binomial coefficient. And then I have the 3 squared so that I have 2y to the 8th. Now, don't forget the 2y. It says y to the 8th. Well, that's the variable part. But this first term of my binomial is 2y, so that entire thing is raised to the 8th power. The first thing I need to know is this binomial coefficient. I can either go look at this 10th row and find 0, 1, 2, or I can say, you know what, that's 10 factorial over 2 factorial, 8 factorial, which is just 10 times 9 over 2, which is 45. So therefore this is going to be 45 times 3 squared is 9, and then 2 to the 8th is 256, y to the 8th, which gives me 103,680 y to the 8th. So my coefficient for this term is that 103,680. That's what I was being asked for. But this makes things a lot easier if I'm just asked for a single value. I don't have to do the entire expansion. Now let's go back and look at that last example. Let me find my page. Here we go. Last two examples. So for this one, we're asked to find the coefficient of x to the 7th in this expansion of 3x minus 1 to the 10th. Well, if I want x to the 7th, and I've got starting with 10, that means this value for j is going to be 3. So I have negative 1 cubed, and then I have 3x to the 7th. Alright, well, 10, my binomial coefficient would be 10 factorial over 3 factorial, 7 factorial, and then I've got a negative 1 because negative 1 cubed, and then 3 to the 7th x to the 7th, if I want to break it down that way. So this binomial coefficient is going to be times a negative 2,187. What is my binomial coefficient? If I go down here and I find row where I've got row n equals 10, and I go choose 0, choose 1, choose 2, choose 3, my binomial coefficient is 120. So I have 120 times negative 2187 times x to the 7th. So my coefficient here is a negative 262,440. That's the coefficient on that x to the 7th term. Okay, last one. Find the 7th term of the expansion of x plus 3 to the 8th power. Well, you've got to kind of think through this and see, okay, what is the 7th term? My first term is going to be x to the 8th. So to the 8th, 7, 6, 5, 4, 3, 2. My y squared term is what we're looking for. If I'm looking for my y squared term, that means my binomial coefficient is 8 over 6, so that this constant is 3 to the 6th, and then I have y squared. Well, what is the binomial coefficient 8 to the 6th equal to? I can either look at my Pascal's triangle, or I can say 8 factorial over 6 factorial, 2 factorial. That's 8 times 7 times 6 factorial over 2, which gives me 4 times 7 is 28. So my binomial coefficient is 28, and then I've got 3 to the 6th power. That's 729 y squared. And when I multiply that, I get 20,412 y squared.